In this video, I'm going to show you the different ways that you can calculate the equilibrium concentrations. And the different ways you calculate them depend on what information you're given. So let's start with something simple. If you're given the equilibrium constant and all but one of the equilibrium concentrations of the reactants and products, you would solve it in a very simple way by setting up the equilibrium constant expression and then just substituting in the values. So let's say we have an equilibrium mixture, so it's at equilibrium. The concentration of the COF2 is 0.255 molar, and the concentration of the CF4 is 0.118 molar. What's the equilibrium concentration of the CO2? So I'm going to set up my equilibrium constant expression. I'm going to always start with this, so I know what I need to fill in. So my equilibrium constant expression is here. I have the products over the reactants and the coefficient squared when I have a 2 for a coefficient. Now I'm going to substitute in the values that I know. I know my equilibrium constant is 2.00. I'm given that information. I don't know the concentration of my CO2, so I'm going to leave that as an X. The concentration of the CF4 is 0.118 and the concentration of the COF2 is 0.255, and I'm going to square that because the coefficient for the COF2 is 2. Now all I'm going to do is simplify this and then solve for x. So 2.00 is equal to x times 0.118 over, and then I'm going to square the bottom of that fraction. The 0.255 squared is 0.0650. Now I'm going to take 0.0650, multiply that by 2, and set that equal to 0.118x. So 0.0650 times 2 is 0.130. That's equal to 0.118x. Now I'm going to divide both sides by 0.118. So then I get x by itself. So x is equal to 0.130 divided by 0.118, which is 1.10. And that is the concentration of my CO2, the equilibrium concentration of my CO2. So this is the process that I use when I'm given the equilibrium constant and then the equilibrium concentrations of everything else except one missing concentration. Now, what if I'm given the equilibrium constant and initial concentrations? The way that I go about doing these is I have to set up an ice table or an ice box. So a reaction mixture at 2000 degrees Celsius initially contains some nitrogen, 0.200 molar nitrogen, and 0.200 molar oxygen. So we have these ingredients and we have no products. So it says find the equilibrium concentrations of the reactants and products at this temperature. So we are given initial concentrations and we need to find equilibrium concentrations. Notice here how I start out only with reactants and I have no products. I'm going to set up a Q expression to show you what that would look like. Remember, Q is set up the same way as K, reactants over products, and Q is equal to 0. And 0 is less than 0.1, so our K is greater than Q, which means the reaction will shift towards the products, meaning we're going to be getting rid of reactants and adding products. So the changes should be negative for my reactants and positive for my products. Finally, I want to express my equilibrium concentrations in terms of X, so I did that right there. The next thing I want to do is set up my equilibrium constant expression. So the equilibrium constant is equal to NO squared over N2 multiplied by O2. I'm going to substitute the values that I know into this equilibrium constant expression. So I know my equilibrium constant is 0.1. I know the concentration of NO is 2x, so I square that. And then I know the concentration of my N2 and my O2 are 0.200 minus x. So if I multiply those two together, I get 0.200 minus x squared, which is really handy because I have the numerator and a denominator squared. All I have to do to solve for x is take the square root of both sides of this. So that's what I do. I take the square root of the left-hand side and the right-hand side of the equal sign, and that gets rid of the square values on the right-hand side. So what's the square root of 0.10? Well, it's 0.316. That's going to equal 2x over 0.200 minus x. Now I'm just going to distribute that 0.200 minus x and multiply that by the 0.316 and set that equal to 2x. So I'm essentially just cross multiplying here. So 0.316 times 0.200 is 0.0632. Subtract 0.316x, set that equal to 2x. So I just cross multiplied there. Now I'm going to subtract, or I'm going to add 0.316x to both sides. So I get 0.0632 equals 2.316x. I'm going to divide both sides by 2.316 so that the x is all by itself. So I get 0.0632 divided by 2.316. That is going to equal 0.0273. Now that's my x. The last thing I need to do is I need to actually use this x to solve for the concentration, the equilibrium concentrations of the reactants and products. So I'm going to find the concentration of the nitrogen by taking 0.200 minus x, which equals 0.173 molar. And that's the concentration of the N2. The concentration of the O2 is exactly the same because we have the same initial concentrations. So the concentration of the O2 is 0.173 molar as well. The concentration of the NO is going to be 2 times x. So I take 0.0273 times 2 and I get 0.0546 molar. So 0.0273 is the amount of the concentration that is lost by the reactants and gained by the products. All right, here's a slightly different type of problem, but we're still going to be solving for the same thing, the equilibrium concentrations of different products and reactants. So we have a 1 liter flask filled with 1 mole of H2 and 2 moles of I2 at 448 degrees Celsius. So we're going to put our initial concentrations in. Now, the concentrations are in moles per liter. So if I have 1 mole in 1 liter, I have a concentration of 1.0 moles per liter. So we have to keep in mind we're always putting in concentrations. So we have 1 mole per liter of H2, 2 moles per liter of I2, and no products. That means that our K is greater than our Q, so the reaction will proceed to the right, meaning the products are going to be positive change and the reactants are going to be a negative change. So I'm writing in my equilibrium concentrations as they relate to X. I don't know that X value, that's my unknown, but I can use that to help solve for the equilibrium concentrations. The first thing I'm going to do is set up my equilibrium constant expression. I would recommend doing this every single time. Don't try to just wing it and plug in some information. It's just good to get everything labeled and out there. So my equilibrium constant expression is there. And now I'm going to substitute all my values in. So my equilibrium constant is 50.5. That's going to equal 2x squared over 1 minus x times 2 minus x. So I get 50.5 is equal to 4x squared. And then I have to do FOIL. So the first is 2, the inside and the outside is 3x, and the outside is x squared. This is going to be a problem for me. I can already see that. So I have 50.5, and I'm going to distribute that. I'm going to cross multiply just like I did in the last problem, but this time I'm multiplying by I'm distributing 3 different values. So I have 50.5x squared minus 151.5x plus 101 equals 4x squared. I'm going to subtract 4x squared from both sides, and that gives me 46.5x squared minus 151.5x plus 101 equals 0. I think you may know where we're going with this, but unfortunately we have to use the quadratic formula to solve for this problem, to find our x values. So remember that quadratic formula, that you maybe used in algebra class. Negative b equals plus or minus the square root of b squared minus 4ac over 2a. I'm assigning my a, b, and c values so that I can plug those into this awful formula and find my x values. So a lot of math here. My b is 151.5. Actually, my negative b is 151.5 plus or minus the square root of that negative 151.5 squared, which is 22,952, minus 4 times a times c, which is 18,786. Now I'm going to take that all over 2a, which is 93. So now I have 151.5 plus or minus, and I'm going to type into my calculator the square root here, the square root of 22,952 over 18,786. Which is equal to 64.5, and that's all over 93. I'm going to solve this two ways here. I'm going to solve it where I have 151.5 plus 64.5 over 93, and that's going to give me x equals 2.32. And now I'm going to solve for 151.5 minus 64.5 over 93. And that's going to give me x equals 0.94. So which one of these x's is valid? Well, now we have to stop using some math and start using some chemistry. So if I take the first x, 2.32, and I actually put it back into the equilibrium unknowns there, I get negative equilibrium concentrations. You cannot have a negative equilibrium concentration. So I can remove this as an option for my x. Now my x that remains is 0.94. So if I plug 0.94 into my equilibrium concentration with the unknown, I get the concentration of H2 is 1 minus 0.94, which is 0.06 molar. The concentration of my I2 is 2 minus 0.94, which equals 1.06 molar. And the concentration of my HI is 2 times 0.94, so that equals 1.88 molar. So it's rare that you would need to use the quadratic formula, but in case you do, this is how you would perform that operation and how you would process the results. Now this is the last type of problem that you will encounter, and this is one where we get to simplify. We get to make some assumptions, simplify, and then go back and check to see if our assumptions were correct. So all I'm doing right now is I'm recording what I'm given, the equation, my initial concentrations. So notice I have only reactants, I have no products. Because I have only reactants and no products, my reactants are going to be negative and my products are going to be positive. So I'm going to just keep continue to fill this out. And then I'm going to write my equilibrium constant expression, which is equal to the concentration of H2 squared times the concentration of S2 over the concentration of H2S squared. Now I'm going to substitute in the numerical values. So 1.67 times 10 to the negative 7th is equal to 2x, which was my concentration of H2, and that's squared, times the concentration of my S2, which is x, all over H2S squared, which is 0.0250 minus 2x, all squared. Now here's where I make an assumption. And I can only make this assumption because the Kc is so small. When you're dealing with a very, very, very small Kc and you're just given reactants, it means you're not going to form very much product. It means this stuff does not react and produce very much. Our Kc is so small. because our Kc is so small and our amount of product is so small, we can say, all right, well, the 2x is also very, very, very small. And if I take a big number, a pretty big number, 0.0250, and subtract a very, very, very small number, it's almost like it didn't even happen. So what can I do? I can just pretend like it didn't happen. So I take my 4x cubed over 0.0250 squared. I pretty much ignore the minusing of the 2x, the subtracting out of that 2x, because that 2x is just so small. So what I end up with is 1.67 times 10 to the negative 7th is equal to 4x cubed over 0.000625. I'm going to cross multiply here and take 0.000625 times 1.67 times 10 to the negative 7th, and I get 1.044 times 10 to the negative 10th equals 4x cubed. Now I'm going to divide both sides by 4, and I get x cubed is equal to 2.61 times 10 to the negative 11th. Now I'm going to take the cube root of that to solve for x. So x is equal to 2.97 times 10 to the negative 4th. The last thing I need to do is I need to substitute that x in for my equilibrium concentrations. So I take that x and I just put it right in there in those equilibrium concentrations. So the equilibrium concentration of the H2S is 0.0250 minus 2x. And my x is 2.97 times 10 to the negative 4th. Don't forget that. So I get 0.0244. So I subtracted very little from that. That tells me that the H2S barely reacted. Barely any of it went away. So the concentrations of my H2 and my S2 should be very, very small. So the concentration of my H2 is 2x, which is 5.94 times 10 to the negative 4th molar. And the concentration of my S2 is 2.97 times 10 to the negative 4th molar. So I have the concentrations of all three species in this reaction. Now the last thing that I need to do is I need to verify that the assumption I made at the beginning was okay. So I need to compare the 0.0250 with the 2x and make sure that the difference between those two is less than 5%. So I could assume that taking out that 2x was okay. So what I'm going to do is set up a ratio here, a percentage. 2x over 0.0250 needs to be less than 5%. So is it less than 5%? I plug in my x and multiply it by 2 and divide that by 0.0250, and I get, and if I multiply by 100 to turn this into a percentage, I get 2.38%, which is less than 5%, which is good. So making this assumption was okay. So hopefully you were able to see all of the different ways that we can find equilibrium concentrations for different reactants and products. One way where we're given the equilibrium constant and equilibrium concentrations of all of the reactants and products but one, and we're asked to solve for that one missing concentration. And then other ways where we are given initial concentrations and the equilibrium constant, and we need to set up ice boxes and solve for those equilibrium concentrations by solving for x and then substituting x back in for those equilibrium concentrations.